Okay, now we're going to do 6.2. We're going to call this 6.2a because this is going to take, look at this, confidence. This is going to take a couple of videos, maybe more than two, to actually learn how to construct a confidence interval for a population proportion. But the name of this section is 6.2, constructing a confidence interval for a proportion. So the first thing we need to ask ourselves is, what is a C% confidence level? When we do confidence intervals, we are usually going to assign them a confidence level. C represents that confidence level. This is the C. C is usually going to be usually put this. This is usually going to be a 90%, 95%, or a 99%. But we could do it with any confidence level between 0 and 100%. You'll learn later why it's important to be a relatively high number. But right now, the most common of all is a 95% confidence level. But these others are also common, so that you could very easily see, I'm just going to bold that, you could very easily see a 90% confidence interval, a 95%, or a 99%. And we'll talk about what the confidence level is in just a few moments. But a confidence interval is exactly what we're saying, an interval, which means it's a range of numbers that has a minimum or a lower bound. We'll call this a lower bound instead of a minimum. And an upper bound this interval estimates the true population proportion. What we're trying to measure. It estimates the true population parameter. And what we're saying when we construct this confidence interval is that we estimate the true population parameter, the population proportion in this case, falls somewhere in this interval. We don't know exactly where. It is just as likely to be very close to the lower bound as it is to the upper bound. It may be in the middle. It could be anywhere in there. When we construct this interval, an important thing for you to know is that we are not saying it's more likely to be in the middle. All we're saying is that we estimate the true population proportion falls somewhere in this range, in this interval, between the lower bound and the upper bound. That's what a confidence interval is. It is assigned a confidence level, and it's built by using a sample proportion, So we're going to do a p hat, and then we're going to add and subtract to get that upper bound and that lower bound. We're going to add and subtract a margin of error. I'm going to call it MOE, margin of error. So at the center of this confidence interval is always going to be a sample proportion p hat. And the lower bound is going to equal p hat minus the margin of error. And the upper bound is going to equal p hat plus the margin of error. When we get onto the equation in a few moments, we're going to talk about why or how to construct that. The lower bound is p hat minus, yes, okay. Now the confidence level, like we said, usually 90%, 95%, 99%. So if you remember, we talked about the sample distribution. We talked about the distribution of every possible sample of size n, and we could get a p hat, a sample proportion, for every possible sample of size n. So if we take every single one of those samples from the sampling distribution and we add the margin of error to get the upper bound for a confidence interval and subtract the margin of error to get a lower bound for a confidence interval, then we have just as many possible confidence intervals as we have sample proportions in our sampling distribution. And we could construct a confidence interval based on every single possible sample proportion in our sampling distribution. So there's the same number of potential confidence intervals that there are p-hats in our sampling distribution. And each one of those p-hats in the sampling distribution is going to be associated with a particular confidence interval. That's where we're going to apply the confidence level. When we set the confidence level at 90%, that means that 90% of all of the possible confidence intervals will contain the true population proportion. When we set at 95% the confidence level, then we are saying that approximately 95% of all of the confidence intervals based on the sample distribution are going to contain the true population proportion. When we set the confidence level at 99%, we are saying that 99% of all possible confidence intervals with sample size n are going to contain the true population proportion, so that we estimate that somewhere in this range between the upper bound, the lower bound, and the upper bound, we are 95% certain if we're doing a 95% confidence level. There's a 95% probability, because if we take all of the possible confidence intervals, 95% of them contain the true population proportion. If we randomly select one of those confidence intervals, then we are 95% sure that we got the population proportion inside that interval. There's a 95% probability that we randomly selected a confidence interval that contains the true population proportion. That's what a confidence interval is. When we say we're doing a 95% confidence interval, it means that we are 95% likely to construct a confidence interval that contains the true population proportion if we satisfy certain conditions for inference. And that's what we're going to look at on the next video, those conditions for inference. But our confidence level usually going to be 90%, 95%, or 99%. But we could set it at 80%. I don't know why you would want to do that, but you could set it at 85% or 92%. You could set it at any proportion you want between 0 and 100. 100 might be a stretch if we don't know the range. But if you knew the range of your possible, well, it's a proportion, yeah. So a 100% confidence interval would end up being from 0 as your lower bound to 100 as your upper bound. That would be a 100% confidence interval. It would contain every possible proportion. That's what a C% confidence interval is. A 95% confidence interval is an interval with a lower bound and upper bound that has a 95% probability of containing the true population proportion, because we selected that one interval from all the possible intervals at random, and we know that 95% of all the possible intervals contain the true population proportion. That's what a C% confidence interval is. Let's move on, because we're going to have an equation for a C% confidence level. Now, I thought in Google Slides that we had a way to insert an equation. There's the equation right there. Those are shapes. We're not looking for a shape. Okay, so I'm going to do the best I can here. Let's see if we can draw, maybe. I swore we had a way to do an equation, but we sure do not seem to have one. Okay, let's go find one on Google real quick.
Can I have your attention, please? If you are a virtual teacher, You will be in a meeting at 2:45 in the cafeteria with Dr. Riggins. Thank you.
Here we go. This is going to be, well, the equation. The equation for a C% confidence interval for a population proportion is going to be your p hat that's your population, or sorry, your sample proportion, plus or minus the z. I'm going to tell you what the z is here in just a few moments. I usually, when I write it, denote it as z star. And then this is going to be, this should look really familiar to you after our sampling distribution unit, but it's going to be the square root of p hat minus, or times 1 minus p hat, all divided by n. So what are those parts of that equation? The p hat is your sample proportion. Whatever your sample was, whatever your proportion of your successes were, that's what's going to go for the p hat. And remember, we're using this equation to estimate, or to create an interval that estimates the value of the true population proportion. So we don't know the true population proportion. The z, or what I'm going to call z star usually, is going to equal what we call a critical value. And what it really is the number of standard deviations away that we need to make this margin of error big enough, large enough to include 95% of all, or so that 95% of all of our confidence intervals include the true population proportion if we're doing a 95% confidence interval, or 90% of the confidence intervals. The margin of error is large enough to contain the true population proportion if we're doing a 90% or like 99%. This z star, I'll show you how to calculate it in the next video, but we're going to calculate this z star for critical values. Now, I told you we usually do 90%, 99%, or 95%. So z star for a 90% confidence interval, z star is, we're going to go ahead and, these certain values we really should have memorized, we should know, because they're going to be very common. 1.64 for a 90% confidence interval, 1.96 for a 95% confidence interval, and 2.58 for a 99% confidence interval. We may be asked to construct a confidence interval for 92% confidence level, and I'll have to show you how to do that, but I'll do that in the next video. But these are the common ones for the 90%, the 95%, and the 99%, the confidence levels. And the calculator, when we do this, you could just set the confidence level, and it doesn't have to, you don't have to have the z star, but you'll often be asked to present the z star, the critical value, so we need to know how to do that. That's the z star. The square root of p hat times 1 minus p hat all divided by n. That looks really familiar. It looks like the standard deviation of the confidence level, or the sample distribution we did in the last unit. And we're going to call that whole square root thing, all that square root stuff, the standard error for the confidence level, for the confidence interval. It's actually an estimate for the standard deviation of the sampling distribution. But since we don't know the population proportion, we don't know the standard deviation. So we're going to use our sample proportion to estimate the standard deviation of the population of the sampling distribution for the p hats. So we are going to estimate that. We're going to use the p hat for that estimate. So the standard error for this sampling distribution, or p hat, and altogether, the z star times the standard error, we're going to abbreviate standard error as SE. When we multiply the z appropriate to our critical, or for our confidence level, times the standard error, that equals the margin of error. That's what we add to p hat and subtract from p hat to get our upper bound and our lower bound. this is the equation for a confidence interval for a population proportion. The p has a sample proportion. The z star is the critical value, and these are the common z stars that we'll use. I'll show you how to find uncommon ones. The standard error is all of this under the square root and the square root of p hat times 1 minus p hat divided by n. And then when we multiply the z times standard error, that gives us the margin of error, the amount over and above our sample proportion that we're using to create the confidence interval for the estimate. And so to summarize, the confidence interval is an interval that we are C%, C's our confidence level, certain contains the true population proportion that we're trying to estimate. The confidence interval is made up of p hat plus or minus z times the standard error. And we saw the equation just a moment ago, what that all looks like when we put the symbols in there. Okay? And this means that at the center of your confidence interval is always going to be your sample proportion. So sometimes in a multiple choice question, they will give you a confidence interval and ask you to identify the sample proportion. It's just the average of the lower bound and the upper bound. They may ask you to identify the z for a particular confidence level. I'll teach you how to do that in the next video. But this confidence interval is just a way that we estimate. We come up with an estimate for the true population proportion.